and Kyle will start the timer when you start talking. So, will you keep an eye on that, Brandon? And if the red light goes out,
Hey,
will
quit,
you?
Max.
Oh no, don't do that. Quit.
Quit.
Just keep an eye, and if the red light goes out, will you just start it again?
Which
then
red
I can
light?
piece together.
Just quit.
I'll
Yeah.
start it.
Oh,
Okay.
there I see.
That'll be your
Do you
job.
see the red light? Or Kai, do you mind?
Yeah, I'll look at
Okay. Thank you so much, because that happened yesterday and nobody saw it happen. So if you see the red light go off, just turn it back on. Thanks. Sorry about that, Max. Thank you.
Alright, we ready?
Yep.
Alright, I'm Max Magee. This is my TED Talk on fusion energy technologies. So, my guiding research question in this project was, what are the engineering constraints to creating a sustainable and scalable fusion energy source? And what technologies are working to achieve this? So to start off, let's define what fusion is, because not everyone knows what it is. So fusion is the process in which stars create energy by fusing light elements together. So as you can see in this diagram, we take deuterium, an isotope of hydrogen, and tritium, an isotope of hydrogen. They fuse together to create helium-4, a neutron is released, and energy is released. This neutron decays into energy along with the energy released. Now the mass of the helium-4 is slightly less than the mass of the tritium and deuterium that were originally in the equation. So this is Einstein's famous equation, E equals mc squared, where mass is converted to energy. So for the last 70 years, humanity has been trying to harness this energy to create a sustainable and scalable energy source to power our world. This reaction releases 4 times the amount of energy as a nuclear fission reaction, which the energy density of this is off the charts. So it's no wonder that we are pursuing this to try to make it a reality. So to get an idea of what a fusion reactor looks like, we're going to watch this short video. So this is a plasma pulse in a company in Europe called Tokamak Energy. And basically this is one of their demo colorized footages of a plasma pulse that they did a couple months ago. So basically this is where the deuterium-tritium reactions are happening, and they are trying to get to a point of where they can get more energy out than they're putting in. So this is just to give you a quick idea of what it looks like and what we're trying to achieve. But the real question is, why is this important? So energy is our most important resource. It is everywhere in our world, from manufacturing, lighting, heating. The United States is an energy-dependent society. And currently our energy makeup contains 40% natural gas, 21% renewables, 20% nuclear, and 19% coal as of 2020. So energy is a highly debated political topic. There's tons of policy behind it, and it's really a crazy issue. There's so much policy going into it. So unfortunately, all of our energy sources currently have drawbacks. Natural gas and coal release CO2 emissions, and supplies are running out depending on what you look at, with many countries looking to decarbonize and use more renewable sources, but these renewable sources aren't so great either. They have very low energy density, they take up lots of land, they have intermittent power, and honestly cannot be used to fully power our world. Nuclear, on the other hand, faces drawbacks such as large investment, public policy, and proliferation for building warheads out of. So overall, there's no one energy source to rule them all. But that's what fusion is trying to do. So in the United States, the industrial sector for energy is predicted to go up in recent years. This is mostly due to the AI boom, data center, and computing needs. This is a graph of the United States, but other countries, other third world countries, are also starting to energize and become more energy dependent. So there's definitely a need for energy here. There needs to be some way where we can have an energy source that is renewable, the fuel is abundant, releases 0 to no CO2 emissions, safe, and high in energy density. So this is where fusion energy comes in. This is what we've been trying to achieve for the last 70 years with mild success. So fusion, the core challenges. So there's a lot of conditions that go into creating a fusion reaction. It requires extreme conditions to achieve. Usually with temperatures exceeding 150 million degrees Celsius. So there's a lot going on here. Temperature's our first one. The temperatures required to sustain these reactions are extreme. There's no materials that can currently contain these, so it's mostly done with magnetic fields. Confinement time is another one. You need to be able to confine the reaction for a long period of time. And for a commercial reactor to be viable, it needs to be running 24 hours a day, 365 days a year, for the most part. So that's another big one. How can we sustain this reaction for a long enough time? And another one is plasma density. How can we make sure that the density of these plasmas is not collapsing in on itself and is dense enough for fusion to occur? So this is known as the Lawson criterion, also known as the triple product rule. These are the three main limitations to fusion. So all these fusion reactors are trying to overcome temperature, confinement time, and plasma density constraints. So that's what we're going into here when we're looking at these technologies. So the first technology that I examined was tokamaks. This is a historical approach to fusion. There are about 100 institutions worldwide who have a tokamak, have built on it. They were invented in about the 1950s in Russia, and basically it works in like a toroidal donut shape where plasma is contained in a donut, basically, to the point where these fusion reactions can occur. So the great thing about this technology is that it's super well researched. The amount of data, scientific publications, and overall scientific knowledge on these technologies is immense. We've been doing it for 70 years, and our tokamaks continue to get only better and better. Now, the main problem with tokamaks is that recently the progress has slowed down. In the 1990s, tokamaks looked like they were going to win the fusion race, that they were going to be the technology to power the world. Unfortunately, that progress has slowed. Does not mean that it could still be the technology to win, it is slowed. For a fusion reaction to work in a reactor, you need to be able to get more energy out than you're putting in. This is known as burning plasma. So the only burning plasma that we've ever achieved was at the Lawrence Livermore National Laboratory in 2022. So for a burning plasma to work, basically you need to get your fusion fuel to a point where it becomes self-sustaining and then can activate other fuel to continue to feed the reaction. So 2022 is the first time that humanity ever created a burning plasma. So the problem with this technology, it's known as inertial confinement, and basically it uses, the Lawrence Livermore Laboratory used 192 lasers to confine a little fuel pellet to the point where it became burning plasma briefly and released energy, more energy out than was put in. So this was truly huge for the world of fusion. It proved that the physics was there. We have scientific proof that fusion is viable. And since then, they've pulsed this thing about 10 times. Now, the problem with this technology is that the amount of energy, infrastructure, and work to get this reaction to work was immense. It was not scalable, not compact, and likely has very little commercial viability. For our energy source to be able to compete in the modern energy world, it needs to be cheap, reliable, scalable, and dependent. An energy source like this would face the same issues as nuclear fission faces today. Large upfront costs, and may never even pay itself off. However, this is seen more as a scientific experiment. Like going into it, we can do fusion now, let's build something off of this. So will this likely be able to become the energy source that powers our world? Probably not. But the science behind it is there, and it's proven very many things in our world. So now we get to the most interesting energy technology of them all, helion energy. So this is the world's largest private fusion company. So the majority of fusion companies are government funded, national labs, universities, all participating in private research. But helion energy is based out of Seattle and is the first fusion energy company to have a commercial energy contract. So currently, Helion Energy is slated to have an energy contract with Microsoft starting in 2028. Now, there's very many sketchy things with Helion Energy. As a private company, they don't have very much data available. 2028 seems like a very unrealistic timeline. They've not achieved a burning plasma, they've not received net energy gain, but yet they have a slated commercial energy contract to start in 2 years. So they use a pulsed magneto approach where they pulse two plasmas together, fuse in the center coils there, and then they skip the steam cycle and think of like an electric car or a hybrid where you break, you can recover your energy. They're basically trying to do that with the fusion plasma. So overall, it's a very interesting approach. There's lots of data behind it. It's just not accessible. So to the public eye, it's very sketchy to say the least. It's hard to say, will this be the energy of the future? It seems to be. Can I find any data on that? No. So going off of that, we got to compare these three technologies. So there's a whole variety of fusion technologies out there, but I chose these three for their primary functions in society. Tokamaks have long historical approaches, research, data, and lots of different institutions pursuing them. So they're definitely heavily researched, they're looked into, people know what's going on with them. You can directly share your research with other people to improve their tokamaks. So in theory, tokamaks are the most pursued thing, especially ITAR, which is the International Thermonuclear Reactor located in France, which includes many countries from around the world who are trying to make fusion energy a reality. It's not really built for commercial viability. It's more of in the inertial confinement setup where you're trying to make it work. You're trying to make the physics happen first. Trying to be able to get those plasmas to sustain. So it's getting there. Inertial confinement has created a burning plasma. It's going very well. They've proven that energy can be directly recaptured from fusion. Is it going to be a commercially viable energy source? Likely not. So we'll have to see what happens there. And then we go to helion energy. They are directly designing for commercial viability, skipping the whole testing and development phase. They have a slated commercial energy contract, but with the lack of public data, it's hard to say if they will be the technology that powers the future. So where is fusion going? So fusion is known as the technology that's always 30 years away. It should have, since the 1950s, it was like, oh, we'll have it in the 1980s. Then it just keeps getting pushed back decades and decades. Here we are today, in a world where energy is uncertain and there's no single source to rule them all. So the reactors are getting better. They are getting closer to the reactor conditions. And within the next couple decades, hopefully, fusion energy will be here to stay and power our world. Thank you.
tape. We don't usually record the Q&A, so thank you guys for keeping